Hello, everybody. Um, I welcome you. Thank you for coming, everyone. While people are joining, kind of outline the entire ordeal we are doing here. Um, this is our first, or should I say, 0th installment of a series which we are going to be doing. And the series is about creating your own programming language, like your custom one. Like, why would you ever want to do it, right? There's a ton of programming languages in the world and so on and so forth. Well, because that's kind of fun uh, to do. And I believe that if you want to like really understand what's going on under the hood of your favorite language you might be using. Like for me, it's C++, and it may be something else for you. But if you really, really want to be better at using the language, it helps kind of to understand how it works and how it's done from the compiler perspective. So we'll have like a number of those webinars. I think it's about 10 of them, something. And we'll gradually move through the concepts you need to understand to build your own language. And at the end, we will have an interpreter of our custom language, which we will kind of come up with here. So yeah, with that out of the way, let's begin and see where it goes, shall we? Okay, so my name is Yuri. I work at the PVS-Studio company, and we are creating a static analyzer. The most probably famous one is for C++, and we also have different languages. And the static analyzer is, well, basically it's a part of a compiler kind of. Compilers work toward a different goal. Like compilers create a binary code, and static analyzers do the same thing basically as compilers do, and they just tell you if anything is wrong with your code. Okay, so that's me here, and I have like a team of fine people who are eager usually to help me, and that's my team. Okay. During this session and other sessions, if you attend them, uh, you all will be muted just to avoid chaos, like people sometimes on accident or otherwise enable their mics and it becomes kind of messy. If you have any questions or comments, you have a chat in Zoom, so put them there. And at the end, I will read everything, well, within reason, of course, everything that goes there, and I will answer your questions and comments and so on. And yes, I think that's it. And without further ado, as they say, let's go. So as a programmer, you like work with colored words usually on screens, which look kind of like that. This is C++. It could be C or whatever. But the point is, like, you have this source code which you type in almost a human understandable language, mostly human understandable language, and then it gets fed into something, and then after that something has done its part, you will get well, something else. If you are using compiled languages, it will be an executable file or a library or whatever. And if you are using languages like Python, interpreted ones, you will get well, something out of the program's execution. So your interpreter will run the result of this black box in the middle. The result of its work will be converted into some output on screen or something else. And during this series, we are going to be diving deeper into this black box, which is between input and some result at the other end of it. Today, I want to talk about the internal composition of this black box and what to expect and what each part does. So let's zoom in. Here's our black box, which takes in some words and output something else entirely and does some magic. And let's look inside of it. So in order to teach a computer to even try to understand what is written in the text form, you need to perform some certain steps. And the first step usually is done by this component, which is called lexer. So what it does, it takes the input in the form of just source text, and then it divides that input into some logical small pieces. But in our example here, it will see the keyword int first. In the first function, it will see some identifier, it will see parentheses, and so on and so forth. And the job of the lexer is to divide according to some rules. Usually, the input is kind of broken up based on white space characters between different parts of it. So its job is to divide the input into some small parts and to tag them, So it will take a small part of your input, and then it will say, okay, that's a keyword. Okay, that's an identifier. That's an operator. That's semicolon, and so on. So it's a classifier of different things written. And this is needed because the next component, the parser, it needs, in order to turn the source code into something more machine digestible, I guess you can call that. The parser kind of needs this divided and categorized stream of input pre-digested by something else in order to build the syntax tree. What is, well, a syntax tree? We'll talk about that later. And the parser and the lexer are actually, they are two parts of the same thing. So you can conceivably have no dedicated lexer in your whatever compiler you have. And the parser technically can do the things the lexer does. So the parser can go all the way from the source code and character levels. But usually the lexer is like its own dedicated component. It gets separated out of the parser just because of convenience, basically. They all work with the same, both of them work with the same grammar. And the next part after this one will be about grammars. Okay. And the parser, it operates on grammatic rules in order to understand what's written at the input. But grammatic rules, of which we will talk in length later, they do not take all possible things related to a language into account, because languages have not just grammars, but also semantics. So in our case, in this source code there, we have function names, right? We have two functions. And from the just grammatic point of view, those are identifiers, just some names, which are not keywords. But semantically, they are function names. So every word has its own meaning. And that's why in any language which is like more complex, grammatically speaking, than assembly or something, you have to have some kind of semantic component to it. So I use the word sema here because it's what it's called in Clang, which is a C++ compiler, the most famous one probably at the current date. But the idea of it is like it gives you insight into what those words mean and into how like data types in your language work in conjunction with each other and how they fall into the bigger picture. And those, well, three components are usually grouped into something called front end. Front end is the thing which deals of a compiler. The front end is the thing which deals with just converting source code via parsing into some other representation for later stages of compilation or interpretation. And in modern C++ compilers, like in Clang, for example, Clang is the front end and LLVM is the back end usually. I guess you can use something else, but usually Clang and LLVM, they go together. And you technically can use the same, for example, backend for different front ends. So you can parse C++, Fortran, I don't know what else, Rust, different languages, all kinds of them. And as long as you create some sort of unified representation of code between the front end and the back end, the backend just doesn't care what the source language was, so it will work. And that's why you have Clang and Flang and so on. So different front ends for LLVM. Speaking of the backend, this is the component which relates to binary code generation. So the front end chews on the input and provides some other form of that input. And it goes down the pipeline. And eventually, this processed input will be turned into like binary code, for example. The system, the entire thing works like a conveyor belt, kind of. And between the front end and the back end, if we kind of zoom out, zoom in, I guess, we have different kinds of things in this compiler internal structure. You might have some optimization pipeline which pre-optimizes your code before it gets fed into the backend, into the code generator. You might have also an kind of evaluator which is usually related to the optimization pipeline, and they work together because if you want to, like, you really want to have an ability to calculate some parts of the input at compile time. In C++, we even have, like, it got really serious, let's say that. We have context per evaluation right during the compilation, and your entire program can be turned basically into just one return if you're lucky or unlucky. And you might also have some different parts here in the middle. But in this series specifically, we will be talking about front end, and we will build an evaluator at the end. And our backend will be just applying this evaluator kind of to the code and getting a result out of it. So we won't be code generating, we will have an interpreter, and we won't be optimizing because this topic is its own really deep rabbit hole, which kind of will be a really long talk if we try to even understand it. And what's funny, this part here, this between front end and back end, sometimes gets called middle end, which I personally find really, really strange, because, like, really, how can it be end if it's in the middle? Like, okay, who am I to judge, right? And in languages which use like really elaborated compilation process like C++, those parts communicate with each other, because in languages where you can calculate things, even call functions at compile time, if you know all the values you need to know in order to like execute the code, this connection is needed between those two parts. But like I said, we are going to be focusing on just this part. Okay, now I talked about components kind of, and here we will just take a look like as a small demonstration at how they work really. So again, back to our input here. And whenever you feed some input to your compiler, interpreter, whatever, by the way, I'm using those terms kind of interchangeably because they are kind of interchangeable, because the line between things like compilers and interpreters, well, it's really thin. It doesn't really matter to distinguish them. The difference basically usually in the output. So they all work in similar ways under the hood. Okay, so you feed this input to whatever program you use to process it. And let's focus just on this line. And it goes to the lexer, and the lexer, it will go word by word, and it will give you this output. So we have the keyword return, which is a predefined word with a predefined meaning in your language. I don't need a semantic analyzer to know that. The lexer is capable of distinguishing between just identifiers and keywords. You have what is called a literal, is this two of the int type. Usually people sometimes mix up the literals and constants and use those terms kind of to mean one and the same thing. But there is really a distinction. Literals are just values you write in your code. And constants usually, this term is reserved for variables which are immutable. So that's the distinction. I just went on tangent by the way. Okay, so next, it will give us an operator plus. Next, another 2, and a punctuation, this semicolon thing. So if we just feed this return 2 plus 2 line into our thing, the lexer will give us this as a result of its work. And then we go to the next step. We go to the parser and provide it with those small parts of our input into which it gets broken. And usually, there are two approaches to that. Your lexer might go from the first character in your input and to the last one, and break it down all the way and give you a big container of whatever these parts. Or the second approach to creating the lexer is when the lexer will consume those parts one by one. So when it will produce the next piece of output when asked and not in advance. And this second approach is what we are going to be taking, because there's no reason really to go and lex your entire program in advance. Or there are kind of approaches in between when you might cache a small part of your lexer output inside the lexer because you want to be able to look at several parts in advance, but that's related usually to complex things, more complex languages than we will be having here. Okay, so what the parser will do? Well, the parser has a set of rules which tell it how to handle different things it will get as input. In our case, we have the keyword return. So this keyword is unambiguous, and it will tell the parser that we are going to be dealing with a return statement at this point. And then after the return statement typically requires an expression inside it, or it might have an empty expression, like you can return something or nothing. In our case, we have a binary operator inside. So we will see how it's done, but inside the return statement, we will have a binary expression with a plus operator. It's an additive expression. And we will have two operands of that expression, two literals. Those will be 2 and like 2. And this punctuation mark, it will just get dropped. As you can see, this tree on the right, punctuation is not present there at all. That's because punctuation, like semicolons and stuff like that, as well as white space characters, their role inside a program on a language is to, well, is to separate things, basically. They are separators. And this semicolon at the end, it just tells us that, okay, the statement is done. And taking it into account, like, ever is not needed after we have parsed it. And this construction here is called an abstract syntax tree, or AST. This is what a parser will typically give you after it's done with processing whatever you give it as an input. And we will be building an AST. And, well, it's called abstract, right? Because it does not, it omits details. It will only use like really significant parts to represent your code. And you can kind of look at this tree as a tree, but really typically we will be looking at it as a kind of this thing. So it's a hierarchical structure of different components of the input, which is traversable and which gives us all the tools we need to calculate what's going on there. And in our case, once we build a tree, it will go to our evaluator, which will then calculate different bits of it and give us a result. Okay, so that was kind of an overview, a bird's eye view on what we are going to be doing. And the plan is, like, we have an intro, we've already had it. This thing, I will tell you what it means in a second. So what our next steps are. We are going to look at grammars. Grammars are essential for any compilery thing to work, because grammars, they define a language. If you want to know what is in a language, you need grammars. We will also build our own lexer, and I will show you how it's done. And after we have built a lexer, we will go into parsing then and create an AST for our language. We will also deal with some semantics. Our language will have variables, it will have functions, and it will have types. Data types of variables, which we will be taking into account. And I will show you how semantics work. We will have, of course, functions, which is the entire point kind of doing this. We will overflow types of constructions in our language. So we will have the conditional statements, if and loops, like conditions and loops. And we will be able to return from functions, of course, and call them. So this is related to control flow. Look into that. We will look into data types, and at the very end, we will look into evaluation. And we will create our QR code here. It leads to PVS-Studio trial, which do not kind of blame me for that. They made me to do that, so I guess, yeah. But in all seriousness, if you want to try video and see what a static analyzer for C++ does, you can use that to get a trial version. Okay, and now I will go into a spoilery territory here, mild spoilers, but still. And I will show you what we are trying to achieve. So here's what we will be moving towards. This is going to be our language. What you see here are two implementations of factorial, because factorial is a very, very nice function if you want to test your evaluator. The language will be called toy, by the way, but it's a toy language. Okay, so this one uses recursion. I guess it's the expected way of doing factorials, which most of people kind of do if they need to do it for some reason. And this one is a loop implementation of a factorial function. And we will look at them both and see how they work in our evaluator, which we will be creating. You can kind of see syntax here. So to make things easy on us, I will be using keywords for functions, which I wish C++ had. And yes, by the way, we will be doing it in C++. Our variables will be kind of implicitly auto, as you can do in different languages, and we will infer the type of variable from the initializer. And yeah, functions will also be able to infer their return types from their return statements. And what this is, we'll get there. So yes, as our zeroth part, I think this will do for now. So if there are any questions, let me check the chat. I will try to answer them if we even have a chat here. Okay, no questions so far. Okay, so yeah, I get it. That's just an intro, so probably nobody had any questions. So it's okay. All right, so that's if you join me for the next, I don't know how many months it will take or weeks, you will by the end of our entire series kind of know how to create your own language. And yeah, so I guess that's all for today. But again, it's just an intro, so it was supposed to be kind of on the short side. And I guess that's all I had to say for today. So have a good day and goodbye.